Hello and welcome. I'm Alex, the industrial engineer, and today we are going to learn how to perform regression manually in Excel for the sole purpose of conducting stochastic analysis. Now, the Excel workbook we will be going through today, I created for a professor at my undergraduate university. If you are a student in that class watching this video for further clarification, welcome. If you do not belong to that group, you are welcome as well. There's much to learn in today's video. Our regression model for this video will be predicting the sale price of a home using other descriptive variables provided in the dataset. The specific interpretations will be different for you and your model and the data you have, but the overall method we'll be going over today will remain the same. First, I wanted to explain the dataset we'll be working with today. The city of Troy in Michigan maintains a dataset on all home sales that occur. I scraped all homes sold in the year 2024 for this analysis. Now, data cleansing is an important step of any quantitative analysis, so I'm going to spend some time explaining the steps I have taken. The first thing you should notice are the columns are removed from the raw dataset, which is shown in red here. I noticed that two house styles collectively made up 89% of all records in 2024, which is shown in this graph on the right. These were the colonial and ranch style homes. Therefore, I binary coded a house style colonial variable where a value of 1 means yes, it is a colonial style home, and a value of 0 means no, it is a ranch style home. Let me show this in Excel real quick. So here in the last column on the table, that's the binary variable I was talking about, where you can only have a 1 or a 0, where a 1 is again a colonial style home and a 0 is a ranch style home for any given home in the dataset. I also converted the sale date column to 3 binary season columns. See here there is winter, spring, and summer. The fall season is not present because when you dummy code a variable in this manner, you must drop one of the categories to avoid multi-collinearity between the variables. Now, after all of these changes, there were 588 records remaining, with the home prices ranging from $136,000 to $1.4 million. Yes, we are creating a multivariate regression model today, but we will also be forecasting using this model. That is why I have performed a 80-20 split of this cleansed data, with the blue 80% majority that you see here will be used to train the regression model, while the green 20%, which I'll scroll down for you, this green 20% of the data at the bottom here will be used to test the model's forecasting abilities when this new data is introduced. And we'll go over this more later. This next worksheet simply shows that Excel already has a built-in tool to perform regression, but I highlight the downside of this feature. While it is much faster to create a regression model, the input data is not connected to the output results. This is the core reason why you cannot perform stochastic analysis using Excel's built-in tool. This is what my method today will solve for us. And down here is the Excel output. I will show how this was generated for those who may be confused. So if we go into the Data tab and go all the way to the right to the Data Analysis button, and we find the regression, click OK. This window will pop up. Our Y range will be the home sale price, that is the variable we are predicting. And then the X range will be every other variable in the table. So we would highlight this whole selection all the way down. We would mark labels because we include headers in our selections. And then the output range, which I have just down here. This is what Excel spits out. The method I will go over today will have us manually calculate the green regression coefficients using Excel formulas. so that our input data is connected directly to our output results. Now, the yellow highlighted cells that you see here are all derived from the green regression coefficients. Now, here again is the same training data, but now it is color-coded in a different manner. Remember, this is the 80% majority data we saw previously. Also remember, we are predicting a home sale price, shown here in the first column in yellow. We are going to call this our Y matrix. The rest of our data becomes our X matrix. One key detail here, and this is really important, it's how I added a intercept column here directly next to our Y matrix column, or Y matrix. This is a very key detail, and if you forget to do this, the method I will show will not correct and will give you incorrect coefficients at the end of the calculation. So what is my method? We are going to be manually calculating the regression coefficients using this beta hat matrix equation shown here. And the regression coefficients are also known as beta coefficients. Remember that this is a matrix equation. We have already established what our Y matrix and X matrix is. And Excel makes calculating this equation easy since it has built-in matrix operation formulas available. We need to perform transposing, inversing, and multiplication to complete the equation. Let's see how this was completed below. Actually, let's look at the equation first. So what I'm highlighting now is the first matrix we need, and then this second matrix here. After we obtain both of these matrices, we can multiply them to get our final result. So let's focus on this first part of the equation, x transpose times x inversed. So here we have our x transposed. This is done using the transpose formula, with it showing up here in the formula bar. Then we multiply the transposed x matrix with the original x matrix, and afterwards we inverse the result. We also need to multiply the transposed x matrix with the y matrix, which is done here. And now we have both matrices necessary to calculate the beta hat matrix shown here at the bottom. Now I brought back Excel's regression output to compare the regression coefficients we calculated to what Excel calculated. Notice they are the exact same. I'll highlight both of these now. And this verifies we did the calculations correctly. Now, our input data is directly connected to the output results. Let's demonstrate this by changing the input data above and observing the effects it has on these coefficients in our beta hat matrix. So I go to our original data set. I could change any number in either the Y matrix or X matrix. It makes more sense to change the X matrix, but this is just for demonstration. We can change any number in here. Let's change this 1300 or 1,312 square foot number to 2,000 square feet. Now, if we scroll down, we see our coefficients are changed. They're not the exact same anymore. So this is the real power of the method I'm showing. And now you can apply a stochastic analysis to it. But there's still more to this story. We still need to calculate other important regression summary statistics shown in yellow here. And I'll show this next. Here in the top left corner are the same beta hat coefficients. Now here in the first column of this table is the training data, that 80%. It's the Y values from the training data. In other words, these are the home sale prices that actually occurred. We need to now calculate an estimated home sale price in the second column using our beta hat coefficients, and then we need to compare the difference between them. From here, we can calculate all sorts of error metrics and other statistics about the regression model. From left to right, we have the sum of squares regression, sum of squares residual, which are both used to calculate the F statistic. Then we have the sum of squares total, the mean absolute error, the mean absolute percentage error, the mean absolute deviation, and the mean percentage error. And finally, we have the Durbin-Watson statistic calculation. Let's continue to the bottom of the worksheet. Here we can observe that using the table above, we can calculate the same values Excel generates in its regression analysis, along with other values not included. Now that we have successfully mimicked what Excel does in the background, I need to explain where we are in this process. We have just created a regression model built on the 80% training data. There has been 0 forecasting completed so far. And all of these model stats and error terms only apply to data within the model, or within the 80% of data used to construct the model. We will proceed to the next worksheet to conduct forecasting using the remaining 20% testing data we split off earlier. We're going to observe how well the same regression model here performs when estimating home sales prices of data it hasn't seen before. Here we have a similar table from the last one. The left column shows the 20% testing data, and the second column shows our regression model's estimate of the home sale price using our beta hat coefficients. Calculating the error metrics for this dataset is interpreted in a different manner since we are now forecasting data outside of our training dataset. Let's go see the results. I want to point out 2 of the error metrics, the mean absolute error and the mean absolute percentage error. With the mean absolute error at $52,940, it can be stated that our regression model predicts home sale prices with an average error of plus or minus $52,940. This translates to a 14.74% MAPE value. This is not bad considering the sale prices of homes ranged from $136,000 to $1.4 million in the total cleansed dataset. And now we have successfully completed building the regression model from the training data and then used testing data to observe the forecasting capabilities of the model. Stochastic analysis would be most beneficial in observing the forecasting statistics and error terms by changing the original training input data to assumption cells, but I would like to leave it to you to experiment with. And one last thing I want to touch on is the fact that this data is not necessarily a time series dataset. Recall that I pulled all of 2024's home price records. Therefore, the forecasting was merely done within the same year. So of course, our R-squared value in this case, being 95%, is very high. If you are in the same university course that this video goes along with, you'll be working with a time series dataset and will interpret the splitting of data into the 80-20 or the testing and training differently, as well as interpreting the error metrics differently. With that, I'd like to thank you for watching today's video. If you learned something new, please leave a like below and consider subscribing. Until next time.